My name is John Bixler. The presentation that I'm giving today is energy modeling as a tool for retrocommissioning. Sort of what I'm going to talk about today is I'm going to start with going over some of the definitions that I'm going to use for this presentation. We're going to get into the inner workings of the energy model, make sure everybody kind of understands the basics of how it works. Look at energy modeling in the context of existing buildings. And then, like I said, give you some examples of how I've used energy modeling in the retrocommissioning process. So first, we'll start off with definitions. What I want to lean on heavily today is the ACG definition of retrocommissioning. Retrocommissioning is a term that means a lot of things to a lot of people. To me, the result of that is that it actually doesn't mean anything at all. It's one of my least favorite terms. You can say it to somebody and they will have no idea what you're talking about because it means so many different things to so many different people. The definition that I really want to use, though, is one that's up on the screen now. Performance analysis of a building that has existed long enough to have useful energy data. The reason I like this particular definition for today, at least, is it opens the door to use these concepts, the things we're going to talk about, in a regular commissioning project, right? People always talk about new building commissioning. I don't understand what a new building is, right? It exists. What's the difference between a new building and an existing building? It exists. As long as that new building has been operating long enough to have some sort of useful energy data, you can use some of the concepts I have that I'm going to talk about. So that's kind of why I want to lean on that particular definition. With retrocommissioning, you have really a lot of arrows in your quiver, right? There's a lot of tools. I have some of them written up on the screen. You know, energy modeling, of course, is another arrow that's in the quiver, right? And that's really what I'm here to talk about today. I want to start out by defining energy modeling. And I'm using the Department of Energy definition for a specific reason. Energy models run on a mathematical engine. That engine is developed by the Department of Energy. The Department of Energy continually works on that model, if you will, and they release new engines periodically. I'll talk a little bit more about that in a little bit. As I was putting together materials for the presentation, I stumbled across this definition, or it was from an article. This is excerpt from an article from the AIA, which of course is the American Institute of Architects. I thought it would be interesting to use in this presentation because, by golly, if an architect thinks there's value in energy modeling, I can certainly get a room full of engineers to agree, right? Just a couple of points I want to emphasize here. I have a pointer. This one, the energy model is a tool that can be utilized throughout the design process to test various design options and optimize the performance of the building. In my mind, commissioning and retrocommissioning is more of an operational process. So I like to reframe that particular sentence in operational terms. So if you do that, the sentence becomes, the energy model is a tool that can be utilized throughout the operational process to test various operational options to optimize the performance of a building. I think it's a really cool idea, and I haven't really seen it in practice yet. At some point in time, if somebody gives the owner the energy model, and then the owner's operational team uses the energy model throughout the life of the building to do different stuff. I mean, you could probably dream up all kinds of good uses for that. So energy modeling really is very, very simple from a fundamental level. You have a whole lot of inputs that you put in to the mathematical engine, and that's the engine that's developed by the Department of Energy, and then it spits out some outputs. The outputs, of course, are really the valuable thing. That's what you're after. It's information about the building performance. And a lot of the energy modeling software that comes to mind, Train Trace, eQuest, other products, really function as a graphical interface for all this process to happen. You can go out and you can get the engine directly from the DOE, and you can put in all the inputs through code and then you can look at all the outputs in the code too. I've seen some screenshots of that process. That wouldn't work for me, I can tell you that. So these products like Train Trace, the programs that do energy modeling, give you a nice intuitive interface so that you can input all your inputs. You understand what they are, and then it also gives you a way to view the outputs. Kind of along those lines, sometimes people ask me, what's the best energy modeling software or whatever. The answer is they're really all the same. They're all running with the same engine, and the only difference is the way they arrange the inputs or the outputs. Some programs might be more intuitive for some people versus other programs. I happen to have spent a lot of time with Train Trace, so that's what I default to because I know exactly where everything is in Train Trace, and that's the only reason. It's not because it's better or worse than anything else. One other thing I meant to mention earlier, as I saw somebody taking notes real quick, I've added a couple of slides here and there, primarily towards the end of the presentation, some pictures of examples and things like that. So don't panic if the handout doesn't match the PowerPoint exactly. Just wanted to throw that out there real quick. So here's some examples of what the inputs are for an energy model. I'm not going to belabor this point other than to say, you have to know a lot about your building, and you have to have, weather data, and then you have to know a lot about your mechanical and electrical systems, and you have to, put all that stuff into the energy model, right? So because the outputs of the energy model rely so heavily on the inputs, right? The quality of the outputs depends on the accuracy of the inputs. We very much have a situation where you put garbage into this thing and you get garbage out, right? So this picture is actually my bedroom the other day. Some examples of what the outputs are like from the energy model. Again, these are what you're really after, right? Utility use data, utility cost data, different building parameters, mechanical and electrical equipment information. I want to go over some examples of what the outputs look like. Again, the point of this exercise is to try to give you a good feel for what's coming out of the energy model. So I'm not going to spend an incredible amount of time doing this, but this particular example is the load information for an air handler. So it includes stuff like the cooling coil peak. Hopefully you can read this in the back. I know it's pretty small. And then there's also the cooling space peak, heating coil peak. One thing that's really neat about energy models, I think, I'm not sure exactly how useful it is, but it's one of those geeky engineer things that I think is cool. It's going to tell you the actual time that the peak occurs. So in this particular case, this is saying on June at 3 p.m., the cooling coil peaks, the cooling coil load peaks. The actual space peak occurs in June at 5 p.m. So that's really like neat information, right? This also gives you information on the temperatures that are being simulated throughout the system, so you can follow the system from a psychrometric standpoint. All the airflow information is over here. Here's some engineering checks. This is kind of like the rule of thumb stuff. Yes?
Regarding your peak time, a word of warning to the system. Make sure you compensate that savings time. So all the inputs and all the front end inputs, there's a program for when daylight savings time starts and ends.
Okay, yeah. Yep. That's an excellent point. That's one I hadn't really thought of before, but that is a good point. Yep. Thank you. Yeah, so those are just the rule of thumb things that people look at: percent outdoor air, CFM per square foot, CFM per ton, that kind of stuff. So you can look at that real quick and make sure you're in the right neighborhood. Oh, this slide. I've deleted this slide like 15 or 16 different times. It's like a zombie slide. It always comes back to me. It's ridiculous. All right, so this one is cooling tower analysis. So this particular project had multiple cooling towers, and so this has been data of what the leaving water temperature is. And it's really, in all my practice runs until the very last practice run, I realized that the higher numbers are on the left and the lower numbers are on the right, which doesn't make any sense to me. But So if all these numbers were shifted to the left, meaning if you looked at the BAS and you found that the cooling tower was putting out hotter water than you expected or than what the energy model expected, that might be a good flag that you've got some sort of problem with your cooling tower. That might be a way to use this one. This is a summary of energy consumption. I don't know, people in the back, can you read this at all? Is this, no, yeah? Okay, I see you. Nobody said no yet, so that's good news for me, I guess. What I want to point out about this one is you'll see, so this is energy consumption, and it's broken down to a level that tends to correspond with what you might see in a typical M&V plan for a building, and that's not coincidence, by the way. So this is broken out into heating energy, cooling energy, auxiliary energy, which is like fans and pumps, lighting, receptacles. So a lot of the M&V plans have kind of worked under the assumption that you would take your M&V information and compare it to an energy model. So the sub-metering that the M&V plans tend to recommend that you use corresponds basically to this, right? Where you've got lights, you've got receptacles, you've got pumps and fans, cooling and heating all separated. So this sort of output would be really useful for a building that's sub-metering, and then particularly if it's trying to follow an M&V plan. This is a report this is the report I've looked at the most, just because when I used to do life cycle cost analysis, this was like the first thing I always looked at, and it's just monthly utility cost. It's pretty straightforward, of course. One thing that you can do with an energy model is you can evaluate different rate structures. That's a really easy thing to do. That's one of the inputs is the rate structure, so you can compare different rate structures, and this would be one report to look at to do that. One of the reasons I like it is it's got utility cost per square foot, so you could very quickly understand if your building's in the right kind of neighborhood for what that should be. Whoop. This is one I wanted to show because this is focusing on the electrical demand peak. So this particular building is peaking at 5 p.m. In July. I guess this is where that daylight savings time comment could maybe be important. But it's breaking down the different components of the electrical demand peak. I had a client once who was like, I don't know if they were right or wrong, but they were absolutely convinced that their entire building structure was driven by the electrical demand peak, which is kind of unusual for my neighborhood. By the way, I'm from Iowa. Does anybody know where Cedar Rapids, Iowa is? Holy cow, that's way more than I expected. So that's where I'm from, which is neither here nor there at this point. But anyway, they were just absolutely convinced that trying to drop their electrical demand was the way to go. So like this particular output would have been really, really valuable for that client. So the original purpose of energy modeling was to allow people to make an apples-to-apples comparison of different design options. One of the easiest examples is the idea of, should I put tinting on my windows or not, right? So you can have a baseline version where you have clear windows, and then you could have an option where you have shaded windows, and then you evaluate the differences between the two. What's really good about an energy model is it's going to take into account all the interactions that occur because of a change. So for the window example, in the case of a shaded window, it's reducing the amount of sunlight that comes in during the summer, right? So that's going to lower your cooling load. It also reduces the amount of sunlight that comes in during the winter, so that's going to increase your heating load. The energy model effectively takes that into account. But it also gives you some insight into some of the changes in mechanical equipment sizes that might happen, airflow changes, water flow changes, things like that. Those are all calculated as part of an energy model. But things change when you have an existing building, right? So I guess I want to open this up to you guys. What are some of the differences that you might think of between a building that's under design versus a building that's already been built and operating for a while? So we talked about the idea of of comparing your outputs from your energy model to known data, right? So that's kind of like the calibration process. It is possible to effectively calibrate an energy model. I just want to throw up some examples from different reports I've done. These are meant to illustrate that the calibration is possible. Here's just total utility cost for a building. Here's one where you've got electrical and natural gas broken out. And kind of one of the points I want to make here is that, like for instance in this case, the actual magnitudes don't match up perfectly, but the trend is very much there. So I think that having the trend there is really important. Here's just another building. So I don't mean to give you guys a step-by-step how-to on calibration, but I do want to leave you with the thought of what the key to successful calibration is for an energy model, and it's being really, really stubborn. It's a very iterative process where you change one input and you expect it to make one particular difference, and you find that it totally makes an entirely different difference, and you start digging into it. It's extremely frustrating. It's why my hair is gray. But the really good thing about it is that you learn a lot about how the energy model works through this process, so you at least get a little bit something out of it on the back end. But it's just absolutely not being willing to quit until you have your energy model so its outputs match the historical data. A couple of the examples I'll go through are ones where there was kind of an aha moment, and where we just could not get the energy model calibrated to the existing data. Then all of a sudden we realized something was going on, and then boom, the calibration happened as soon as we made that discovery. So I glossed over it earlier, but one of the things, I'm just going to leave this code up here for a real long time while I talk. One of the things that I glossed over earlier, but I kind of want to talk about, is the idea that the retrocommissioning process is going to share information to the energy model, and then the energy model is going to share information back to the retrocommissioning process. So that aha moment I just described, where all of a sudden the calibration happens, that's an example of the energy model sharing information back to the retrocommissioning process. I really like this picture. I wanted to put it in front of a room full of engineers. The retrocommissioning process is where the rubber meets the road. So in a typical retrocommissioning process, this is my buddy Jason. Jason got the nickname Lunchbox from a trip he had here to Central Florida, and it's a really funny story, but that's not what this presentation's about. So in a retrocommissioning process, you have all these on-site observations, all these things that you're learning about the building, whether you're doing building testing, reviewing trend data, whatever it is you're doing. And you can share that information with the energy model. So you can have those observations reflected in the inputs of the energy model. And then the information that the energy model shares back, there's all kinds of different things. Some of them are up on the screen. I think one important one is you can quantify savings. Another way to look at that is you can quantify the cost. Like, this thing is broken, and this is how much it's costing you per year or whatever. And you can say that with a very high degree of confidence, especially when you have a well-calibrated energy model. The key here, and I think the thing that all your clients are buying when they want to do a retrocommissioning project, is information that helps guide them with the decision-making process. So how are they going to move forward with this building? What do they need to do? You're providing them information to help with that decision-making process. And that's kind of where the value comes from, this process of using the energy model as one of your tools. So now I'm going to get into the home stretch of my presentation, and this is a variety of examples, and we were stuck on that one slide for so long. I'm going to run short on time, so I'm going to go quick through these. I'm going to do a couple, and then I'm going to kind of open it up and let you guys, maybe if you have any examples of your own that you want to share, you can do that. So I'm going to start with a real easy one. This is a building where we're doing a retrocommissioning project, and we found that VAVs with the dampers stuck wide open, right? So they didn't modulate. So who's seen a VAV who's got a stuck damper, right? And we probably all have. In an energy model, there's a entry at the zone level for the minimum flow ratio, which is really the VAV turn down. So if you've got one that's stuck wide open at maximum airflow, then you would just put a 1 in that box. And that's how you use the energy model to quantify the cost of that. In this particular case, the client was looking at replacing a bunch of pneumatic VAV actuators, many of which had failed, with DDC. So we were able to give them really good information about what the cost savings would be by using our energy model. There's a pretty long backstory to this one, and in the interest of time, I'm just going to totally skip it. But the long and the short of it is this is a building where the air was distributed into the space through combination light diffusers. I don't know, has anybody ever seen these before? There's an inlet on top, and then the air blows down over the top of the light fixture and then into the space. Well, the problem with that is all the heat that's generated by a light fixture is conducted directly to the to the supply airstream. So we took some measurements, and we found that the supply air temp increased 5 degrees from the air handler to the outlet, which is pretty darn significant. In the energy model, there is a place for that, duct delta T. So in this particular case, that number should be 5. And that's where it appears in the energy model. This is particularly significant in this building. Again, I'm not going to try not to get into the huge backstory, but this building really had a cooling capacity problem, and this directly affects cooling capacity, and we were able to quantify it very exactly by using the energy model. Here's an example of a building where we had that kind of aha moment that I talked about earlier, where we were trying to calibrate the energy model and we just couldn't get it, and then all of a sudden we made one change and it matched right up. This was an old building built in the 1920s, and it relied on a free return system, which is, I don't know if that's kind of an industry-wide term, but there were openings above the ceiling that allowed the return air to go from a room all the way back to the air handler. There happened to be only one air handler in this particular building. So in the late 1990s, some architects came along and decided they wanted to make the building really safe. So they built firewalls everywhere. So in order to do that, they blocked over all the return air openings, and that was it. So the owner complained a lot about pressure problems in the building, where you would open a door to the stairwell on one floor and you'd have air rushing in, and then on another floor you'd open the door to the stairwell and air would rush out. The air would move so quickly through there that it would knock stuff off the walls, and it was an issue. The building also had really high energy use. It is a 1920s building. A lot of it had original windows, single pane windows where the seals had gone out. You could actually see and hear the glass rattling back and forth in the sash. No air barrier whatsoever in the envelope construction. So what we realized eventually was that there were a lot of areas on the exterior of the building that were negatively pressurized. They were bringing in outside air. In the energy model, we were really confident we had everything set right, and we still couldn't get it to match. So we just started increasing the infiltration value in those zones and just kind of worked it up, and then all of a sudden, boom, the energy model predicted energy use matched the historical energy use. So we were kind of able to quantify the degree to which the infiltration was costing the client money in this particular case. This is kind of a long one, and I'll tell you what, I'm just going to kind of skip it entirely. This is one I do want to try to hit quickly because I think it's always my favorite example of how you can use energy modeling in a retrocommissioning project. This is a building that was only about 10 years old when we did this project. It had a geothermal heat pump system. It was ground coupled. I sort of realized as I was putting this presentation together that maybe isn't a common system everywhere in the United States. So quick background that's pertinent to the story. This system takes heat out of the ground in the winter and uses it to heat the building. During the summer, it puts heat into the ground as you're cooling the building. And so this system really only makes sense in areas where you're taking about the same amount of heat on an annual basis out of the ground to heat the building as you're putting back into the ground when you're cooling the building. Happens to work good where I'm from in Iowa. Probably not such a great idea in Orlando, Florida. In this particular building, the ground had heated up to the point where the heat pumps were starting to trip off. And the maintenance personnel was saying once that loop temp reaches 108 degrees, the heat pump trips off on, the compressor trips off because the water is too hot. So they were actually, in the middle of this project, they were shutting the portions of the building down and sending people home from work. It happened to be a city hall. So that was kind of a bad situation. And we took our energy model, which happened to be train trace, but that's really neither here nor there. And you're able to export the block loads, the annual block loads from train trace. We were able to export those, and then we used some software that was a well field simulator, and we were able to import those annual loads into the well field simulator. That well field simulator also included, like the layout of the wells and the thermal conductivity of the ground, all these different things. And it was able to predict the long-term temperature of the ground loop. And what was really cool was, like I said, the building was about 10 years old. And this graph is trend data from the building. And you can see where it starts to hit that critical line of 108 right there. I think that's maybe 10 days worth of data, so you can see during the day it pops up, and then at night it comes back down a little bit. So that's when they started to have problems. On this graph, this is the output from the well field simulator. And you can see at time 120 months is when you first start hitting that critical temperature of 108 degrees. So that was like a really cool engineering thing, right? We were able to get our well field simulator on the very first try, I might add, to tell us that the well field was going to hit the actual temperature we were seeing 10 years later. We were then able to, through the same process of exporting block loads from the energy model, evaluate some different options, including stuff like add more wells to the system or add a cooling tower, but also some more nuanced things like add tinting to the windows, things like that, other strategies that reduce the annual cooling load, and not only tell the client how much energy they would save, but also what the effect on the long-term well field temperature was. So I thought that was really cool, because that was actually more important to them than anything else, really. So I want to wrap up my portion at this point and just kind of reemphasize this idea that by using an energy model, you can take information from a retrocommissioning project, put it into the energy model, and then take energy model out of the retrocommissioning project, take information out of the energy model, feed it back into the retrocommissioning project, and you've got this really cool cycle that happens. In the end, you get really good information that you can give your clients to help them guide decisions to make for happy clients.